Direct variation. All right, direct variation is a type of linear equation that specifically runs through the origin. Okay, runs through the origin, meaning that its y-intercept is always 0. Okay, that means that instead of our normal y equals mx plus b slope-intercept form equation, we write it as y equals kx. Okay, and that's because b is 0. Okay, if b is 0, we don't need it in there. And we use k instead of m just to show that it is this direct variation equation. To show that, well, I didn't just forget about my y-intercept. I didn't just forget about b. There is no b. Okay, b is 0. So don't get too confused about k. It's the same thing as m. All right, they're both just variables that stand for the slope. Okay, k specifically is called the constant of variation sometimes, but it's still just the slope. Okay, the constant of variation is the slope of a direct variation equation. Okay, it's no different. Well, it's kind of different, but it's different in an easier way. So when we are looking at what, or if a data set is a direct variation equation, we need to once again remember that it goes through the origin and its y-intercept is 0. And that means that we have, for a normal linear equation, we have an initial positive or negative value that a direct variation equation doesn't. Okay, so the example I'd like to use is buying two different types of items. Okay, so for a direct variation equation, okay, it would be buying multiple items of the same type. Each one costs the same amount. So if I buy one apple, it costs me, well, we'll say they're really fancy apples. We'll say one apple costs me $2. Okay. If I buy 2 apples, it's going to cost me $4. And if I buy 3 apples, it's going to cost me $6. It's because each apple is $2. There's no initial price. Okay, so however many apples I buy, I multiply that by $2. That's what I get. That's how much it costs. Okay. Now, pizzas, all right, instead of buying multiple pizzas, now what I'm doing is I'm buying either a 1-topping pizza, right? Here's one with just pepperoni, or I'm buying a 2-topping pizza, and this one's got pepperoni and some sausage on there. Okay, my 1-topping pizza costs $15. All right, so if this was a direct variation equation and there wasn't any initial cost, then my 2-topping pizza would be $30. But it's not. My 2-topping pizza is $16. Okay? And what that is saying is, yeah, it's $1 for an extra topping, but the other $14 is the cheese, the dough, the sauce, the work it takes to make the pizza, the time it takes to cook it. So there's a lot of initial cost that goes into making that pizza. All right? So we can't say that each topping is $15. Each topping is only $1, but there's an initial cost. Okay, this is still a linear equation, but it is not a direct variation equation. Okay, hopefully you understand the difference. The math itself is not too difficult. If you can understand the difference between a linear equation and a direct variation equation. Okay? And when we're given a set of data, all right, there's 2 ways that we can look at it and determine whether it's a direct variation equation. Okay? And remember, we're looking for that line that goes through the origin that has that y-intercept of 0. That will be our direct variation equation. Okay, so our first method is graphing. So we just come over at 2, 1, 2, 3, 4, and 3, 6, 4, 8. And if I made my linear equation to match up, I would see that, yes, this is a direct variation equation because it goes through the y-intercept. Okay. Another way to do that, and while this was pretty quick, pretty easy, because my numbers are nice and small, they're close to my origin, it's easy to graph. Sometimes they won't be, and using ratios is going to be the easiest way to do it. Okay, and in that case, I'm going to take my y and make that my top. Okay, same way I do as a slope or in a slope. So I'd have a 4 over 2, my y value over my x value, and I'm going to see if that's equal to 6 over 3 and 8 over 4. In a direct variation equation, every point should have the same ratio. Okay, so 4 over 2 should be equal to 6 over 3, and it should be equal to 8 over 4. All right. 4 over 2, if I divide both by 2, is 2 over 1. Divide both by 3, 2 over 1. Divide both by 4, 2 over 1. So my ratios are equal, which means that this is a direct variation slope or a direct variation equation, and my slope, or my constant of variation, is 2 over 1. It's my most simplified fraction. Okay, but every point should make that. Okay, it should equal that. Okay. Now, if we look at another one, and you can see I have changed the values in this table, but only slightly. Okay, our table up above was 2 and 4, 3 and 6, 4 and 8, and now I've just increased all my y values by 1. Okay, if I looked at my change, all right, it would be the same. Okay, up here, 2x increases from 2 to 3, so it goes up 1. Y increases from 4 to 6, it goes up 2. That's my slope, 2 over 1. Down here, x increases from 2 to 3, that's 1. Y increases from 5 to 7, that's 2. My slope is the same. My slope is 2 over 1. Okay. The difference is going to be where my line is at. Okay. So if I come over 2, come up 3, 4, 5, over 3, up 7, 4, up 9. Okay, you can see I still have that same slope. My line is still linear. But now, if I draw my line and line everything up, it's not crossing at the origin. It's crossing up here at 1 for my y-intercept. Okay, that means it's still a linear equation, but it is not a direct variation equation. And if I looked at my ratios, 5 over 2, 7 over 3, 9 over 4. 5 over 2 is not equal to 7 over 3, and not equal to 9 over 4. None of these are equal. Okay, if I pulled out my calculator and I figured them out, this would be like 2.5, this would be 2 1/3, and this would be 2 1/4. Okay, so my ratios are changing. My slope is the same, right? I still have a constant slope. It's still linear, but my ratios are different, meaning it's not a direct variation equation.